Now, let us consider another problem as a part of which there are two signals f of t and g of t given. Both the signals f of t and g of t are continuous time and non-periodic signals. Also, please note that g of t is a derived version of f of t. It's given that Fourier transform of f of t is f of j omega and Fourier transform of g of t is g of j omega. We have to find g of j omega in terms of f of j omega. So we can see that g of t can be obtained from f of t by advancing f of t by one sample and compressing along time axis by a factor of 2. From this we can write that g of t is equal to 2 times f of 2t plus 1. So now we can write Fourier transform of g of t, that is g of j omega is equal to integral minus infinity to plus infinity g of t multiplied by e power minus j omega t dt, that is equal to integral minus infinity to plus infinity 2 times f of 2t plus 1 multiplied by e power minus j omega t dt. Now substitute 2t plus 1 is equal to p. That implies 2 times dt is equal to dp. Also t is equal to p minus 1 by 2. From this we can simplify g of j omega as 2 times integral minus infinity to plus infinity f of p multiplied by e power minus j omega multiplied by p minus 1 divided by 2 dp by 2. So this 2 and this 2 get cancelled. From this we can write that g of j omega is equal to e power j omega divided by 2 multiplied by integral minus infinity to plus infinity f of p multiplied by e power minus j omega by 2 multiplied by p dp. We see that the quantity in the brackets is equal to f of j omega divided by 2. From this we can write that g of j omega is equal to e power j omega by 2 multiplied by f of j omega divided by 2. So from the given g of t and f of t signals, we could get g of j omega in terms of f of j omega. Also, we see that if the signal g of t is a compressed version of f of t along time axis, we see that the Fourier transform of g of t, that is g of j omega, is a expanded version of f of j omega in the frequency domain. Now let us consider another problem, as per which it is given that there is a signal x of t which is continuous time and non-periodic. It is given that Fourier transform of x of t is equal to x of j omega, and it is also given that magnitude of x of j omega is even. Then we have to find the correct option out of the given options about the nature of the x of t. That is, x of t is conjugate symmetric, or x of t is conjugate skew symmetric, or x of t is purely imaginary. As per option A, if x of t is conjugate symmetric, we know that x of j omega is real. So from this we see that, so from this we can say that option A is not the correct option. As per option B, if x of t is conjugate skew symmetric, x of j omega is purely imaginary. From this we see that option B is also not the correct option. Now let us pick the option C, as per which x of t is purely imaginary. We know that if x of t is purely imaginary, x of j omega is conjugate skew symmetric. If x of j omega is conjugate skew symmetric, magnitude of x of j omega, that is amplitude spectrum, is even. From this, we see that option C is the correct option. So we can say that if abs of x of j omega is even, one of the possibilities is that x of t is purely imaginary, and we arrived at this answer based on the options given. Now let us consider another problem as a part of which there is a signal x of t which is given as shown in the figure. Please note that the signal x of t is present in the range of -2 to +2 as shown. It's also given that Fourier transform of x of t is equal to x of j omega. We have to find the value of x of j omega at omega is equal to 0 radians per second. We know that x of j omega can be written as integral minus infinity to plus infinity x of t e power minus j omega t dt. On substituting omega is equal to 0, we get that x of j0 is equal to integral minus infinity to plus infinity x of t dt. We know that this quantity integral minus infinity to plus infinity x of t dt is area of x of t with time axis. So from the given plot, we can say that the area of x of t with respect to time axis can be written as 4 into, sorry, 1 plus 2 into, sorry, plus half into 2 into 1, which finally reduces to 5. From this, we see that the value of x of j omega at omega equal to 0 radians per second is 5. Here we got the value of 5, value of here we got the value 5 by finding the area of x of t with time axis, that is the region marked. Now let us consider another problem as per which there is a continuous time domain signal x of t given whose Fourier transform is x of j omega. Now there are two statements given as related to above x of t, that is if x of t is real, magnitude of x of j omega is even. The second one is if x of t is conjugate symmetric, real of x of j omega equal to 0. We have to find which of these two statements are true. As per statement 1, x of t is real. We know that if x of t is real, x of j omega is conjugate symmetric. So x star of j omega is equal to x of minus j omega. From this we can show that magnitude of x of j omega is equal to magnitude of x of minus j omega. So that implies x of j omega is even. So from this we can say that the statement 1 is correct. Now let us consider the second statement as per which x of t is conjugate symmetric. So we know that if x of t is conjugate symmetric, x of j omega is real. That implies imaginary part of x of j omega is 0. From this we can say that the statement 2 is wrong. So based on the properties of Fourier transform, we can say that the statement 1 is correct, statement 2 is wrong. Now let us consider another problem as related to a discrete time non-periodic signal x of n, which has a dtft of x of e power j omega. There are two statements given. The statement one is that if x of n is odd, Then abs of h of e power j omega is even. And the statement 2 is if x of n is conjugate skew symmetric, then real part of x of e power j omega is 0. We have to find which of these statements are correct. Now let us pick the statement 1, as per which the signal x of n is odd. We know that if signal x of n is odd, then x of e power j omega is conjugate skew symmetric, assuming that x of n is real as well. If x of n is conjugate skew symmetric, then magnitude of x of e power j omega is even. So the statement 1 is correct. As per the second statement, x of n is conjugate skew symmetric. We know that if x of n is conjugate skew symmetric, now let us consider another problem as a part of which there are two signals f of t and g of t given. Both the signals are continuous time and non-periodic. F of t has a Fourier transform of f of j omega and g of t has a Fourier transform of g of j omega. Please note that g of t is a derived version of f of t. It's given that at omega equal to 1, magnitude of g of j omega is equal to magnitude of f of j omega, and also at omega is equal to 2, magnitude of g of j omega is equal to magnitude of f of j omega. Then we have to find out the possible relation between g of t and f of t out of the options given. That is, option A is g of t is equal to df by dt. Option B is g of t is equal to f of t minus t naught, where t naught belongs to R. Option C is g of t is equal to e power j omega naught to t multiplied by f of t, where omega naught belongs to R. Option D is g of t is equal to 2 times f of t. So as per option A, if g of t is equal to df by dt, we know that g of j omega is equal to j omega multiplied by f of j omega. From this, we can write that magnitude of g of j omega is equal to omega magnitude of omega abs of omega multiplied by abs of f of j omega. So this is not the correct answer as it doesn't satisfy the given conditions. Similarly, we see that as per option B, we can write that g of j omega is equal to e power minus j omega t naught multiplied by f of j omega. From this, we can say that magnitude of g of j omega is equal to abs of f of j omega, which satisfies the given conditions. So option B is the correct answer. However, let us verify the same with option C and D also. As per option C, we can write that g of j omega is equal to f of j times omega minus omega naught. So this is also not the correct answer. And as per option D, g of we can write that g of j omega is equal to 2 times f of j omega. We see that this is also not the correct answer. So from this we see that based on the given conditions, the possible relation between g of t and f of t is g of t is equal to f of t minus t naught, where t naught belongs to R. Now let us consider another problem as per which there is a discrete time signal given as x of n is equal to 1 by 2 plus 3j whole power mod n. It's given that Fourier transform of x of n is given equal to. x of e power j omega. Now we have to pick the correct option out of the following for the given signal x of n. Option A says that x of e power j omega is equal to x star of e power minus j omega. As per option B, imaginary part of x of e power j omega is equal to 0. As per option C, real part of x of a power g omega is equal to 0. As per option D, none of these. We see that the given signal x of n is complex, and we also see that the given signal x of n even. So from this we see that the given signal x of gen is not real, not purely imaginary, not conjugate symmetric, not conjugate skew symmetric. From this, we can say that the given x of n doesn't satisfy the conditions in option A, option B, and option C, because these conditions are typically satisfied for the cases when x of n is either purely real or purely imaginary, or conjugate symmetric or conjugate skew symmetric. From this, we can say that option D is the correct option. Now let us consider another problem as per which there is a continuous time signal x of t given. It has a Fourier transform of x of j omega. There is another signal x of 5t minus 3 given. Please note that x of 5t minus 3 is derived version of x of t. We have to find the Fourier transform of x of 5t minus 3 in terms of x of j omega. We know that the Fourier transform of x of 5t minus 3 is given as integral minus infinity to plus infinity x of 5t minus 3 e power minus j omega t dt. Substitute 5t minus 3 is equal to p. From this, t equal to p plus 3 by 5 and dt equal to dp by 5. Upon substitution, Fourier transform of x of 5t minus 3 can be written as integral minus infinity to plus infinity x of p e power minus j omega multiplied by p plus 3 by 5 dp by 5, which can be simplified as 1 by 5 integral minus infinity to plus infinity x of p multiplied by e power minus jp multiplied by omega by 5 multiplied by dp, which is as a whole multiplied by e power minus j3 omega divided by 5. From this we see that Fourier transform of x of 5t minus 3 is equal to 1 by 5 multiplied by e power minus j3 5 omega divided by 5 multiplied by Fourier transform of sorry j3 omega 5 multiplied by x of j omega by 5. So the derived version of x of t, which is x of 5t minus 3, has a Fourier transform of 1 by 5 multiplied by e power minus j3 omega 5 multiplied by x of j omega by 5. Now let us consider another problem as per which there is a discrete time signal x of n given. It's given that x of n has a dt of x of e power j omega. There were two statements given as related to the statement. As per statement 1, if x of n is real and odd, then magnitude of x of e power j omega is even. And as per statement 2, if x of n is conjugate skew symmetric, real part of x of e power j omega is 0. We have to find which of these two statements is correct. Now let us pick the statement 1. As per which x of n is real and odd, it means that x of n is conjugate skew symmetric, which implies that x of e power j omega is purely imaginary, which means that real part of x of e power j omega is equal to 0. So from this we can say that we can't comment on even property of abs of x of e power j omega. So the statement 1 is not correct. As per statement 2, x of n is conjugate skew symmetric as before, which implies that x of e power j omega is purely imaginary, which means that real part of x of e power j omega is 0. From this we can say that the statement 2 is correct. So based on the given x of n, we can say that the statement 1 is not correct and statement 2 is correct. Now let us consider another problem as per which two signals x of t and y of t are given as shown in the figure. X of t is present in the range of -2 to +2, and it has a maximum value of 1 at the instant t is equal to 0. Now there is another signal y of t which is plotted as shown. It is all present in the range of 0 to 2, and at instant t is equal to 1 it has a value of -1. Sorry, 0 to -2. At instant -1 it has a value of -1. It's given that x of t has a Fourier transform of x of j omega, and y of t has a Fourier transform of y of j omega. It's given that y of t is a derived version of x of t. Then we have to find y of j omega in terms of x of j omega. We see that y of t can be obtained from x of t by advancing x of t by 2 seconds, then compress along time axis by 2, then inverse the amplitude of x of t to get y of t. So we can write that y of t is equal to minus of x of 2t plus 2. But this is a relation between y of t and x of t, whereas we have to find y of j omega in terms of x of j omega. So we can write that y of j omega is equal to integral minus infinity to plus infinity y of t, which can be written as minus of x of 2t plus 2 multiplied by e power minus j omega t dt. Substitute 2t plus 2 is equal to p to get t is equal to p minus 2 by 2 and dt is equal to dp by 2. So from this we can write that y of j omega is equal to minus 1 by 2 to minus 1 by 2 multiplied by integral minus infinity to plus infinity x of p multiplied by e power minus j omega multiplied by p minus 2 divided by 2 dp, which upon simplification can be written as minus 1 by 2 multiplied by e power j omega multiplied by integral minus infinity to plus infinity x of p multiplied by e power minus jp multiplied by omega by 2 dp. But we know that the quantity present in the brackets is equal to x of j omega by 2. From this, we can simplify y of j omega as minus 1 by 2 multiplied by e power j omega multiplied by x of j omega by 2. So from the given x of t and y of t, we can get y of j omega in terms of x of j omega as shown. Now let us consider another problem as per which there is a signal x of t whose Fourier transform is given as x of j omega. It's given that the energy of the signal is 10 joules and also the magnitude of x of j omega is plotted as shown. Magnitude of x of j omega is 1 in the range of a to 2. We have to find the value of a based on the data given. We can say that by Parseval's theorem, energy of the signal x of t is given as Ex is equal to integral minus infinity to plus infinity mod of x of t whole square dt is equal to 1 by 2 pi integral minus infinity to plus infinity mod of x of j omega whole square d omega. We know that quantity on the left hand side is 10 joules. From this, we can simplify the quantity on the right hand side as 10 is equal to 1 by 2 pi multiplied by integral a to 2 d omega, which can further be simplified as 1 by 2 pi multiplied by 2 minus a. Upon simplification, this becomes a is equal to 2 minus 20 pi. From this, we see that for the given apps of x of j omega and for the given x of t with the energy of 10 joules, we can say that a should be equal to 2 minus 20 pi. Now let us consider another problem as per which there is a signal x of n which is given as shown in the figure. It has a value of 5 at the instant 0. It has a value of minus 2 at the instant 2. It has a value of 4 at the instant 3. Sorry, value of 3 at the instant minus 4. Similarly, it has a value of minus 2 at the instant 2 and it has a value of 3 at the instant 4. We have to find the value of x of e power j omega at omega equal to pi by 2 if x of e power j omega is the dt of x of n. We can say that x of e power j omega is equal to sigma n sigma n x of n e power minus j omega n. So this can further be simplified as x of e power j pi by 2 because we need to find the value of x of e power j omega at omega equal to pi by 2 sigma n x of n multiplied by e power minus j pi by 2 n. So this is further equal to 3 multiplied by e power minus j pi by 2 multiplied by minus 4 minus 2 multiplied by e power minus j pi by 2 multiplied by minus 2 plus 5 plus sorry minus 2 multiplied by e power minus j pi by 2 multiplied by 2 plus 3 multiplied by e power minus j pi by 2 multiplied by 4. This is upon substituting the values of n in the given summation and we are trying to find out the summation. This can be simplified as 5 plus 3 multiplied by e power j2 pi plus e power minus j2 pi then minus 2 multiplied by e power minus j pi plus e power j pi. So this can be simplified as 5 plus 3 into 2, because e power j2 pi is 1, then minus 2 multiplied by minus 2. This is because e power minus j pi is minus 1. So which upon simplifying becomes 15. Now let us consider another problem, as per which there is a signal x of t given, which is conjugate symmetric, and there is another derived signal given, that is y of t is equal to dx by dt. The Fourier transform of x of t, which is x of j omega, is as shown in the figure. It has a value of 1 in the frequency range of minus 1 to 1. We need to find the area of abs of y of j omega with respect to omega. We know that if y of t is equal to dx by dt, we can write that y of j omega is equal to j omega multiplied by x of j omega. From this, we can write that abs of y of j omega is equal to abs of omega multiplied by x of j omega. But we know that x of j omega is 1 in the range of minus 1 to 1. From this, we can plot abs of y of j omega as shown. Please note that the abs of y of j omega is positive in the range of minus 1 to 1 as shown. From this, we can say that the area of abs of y of j omega with respect to omega as 2 into 1 by 2 multiplied by 1 into 1, which is equal to 1. So from the given data, we can find that area of abs of y of j omega with respect to omega axis as 1. Now let us consider another problem, as per which there is a periodic waveform shown in the figure. The periodic waveform x of t is a square waveform, which is 1 in the range of 0 to t by 2 and minus 1 in the range of t by 2 to t. Please note that x of t has a period of capital T. Now we have to find the second harmonic content in the waveform. We know that by alternate Fourier series expansion, we can find the second harmonic content. We see that the given signal x of t is odd. So as x of t is odd, we know that the TC term a0 is 0 and also an is equal to 0. And we can see that the sign term, the coefficient corresponding to the sign term, bn can be written as 2 by t by 2 integral 0 to t by 2 x of t sine of omega nt dt, where omega n is equal to 2n pi divided by capital T. From this, we can see that dn, the second harmonic, that is for n is equal to 2, can be found out as b2 is equal to 4 by t integral 0 to t by 2 1 multiplied by sine of 4 pi by capital T multiplied by t dt. But we see that upon finding this integral value, the value of b2 is equal to 0. From this, we can say that the second harmonic content in the given x of t is 0. Now let us consider another problem as per which there is a continuous time non-periodic signal given which is x of t as shown in the figure. X of t takes a value of 1 in the range of -1 to +1. We need to find the value of integral minus infinity to plus infinity mod of x of j omega whole square d omega, where Fourier transform of x of t is written as x of j omega. We know that by Parseval's theorem, energy of a signal is given as Ex is equal to integral minus infinity to plus infinity mod of x of t whole square dt, which can further be written as 1 by 2 pi integral minus infinity to plus infinity mod of x of j omega whole square d omega. From this we can see that the required quantity R is equal to 2 pi into energy of x. We see that the energy of the given signal is 2. From this the required quantity is equal to 2 pi into 2, which is 4 pi. So by using the Parseval's theorem, we can say that integral minus infinity to plus infinity mod of x of j omega whole square d omega is equal to 4 pi. Now let us consider another problem as per which there is a continuous time periodic signal x of t given and its complex Fourier series representation is given as x of k. If x of 2 is equal to 3 plus 2j, we need to find x of minus 2. Please note that the given signal x of t is real, continuous time, and periodic. We know that from the nature of the frequency representation of the signals, if a signal x of t is real, then its frequency representation is conjugate symmetric. Here the corresponding frequency representation is complex Fourier series representation. So we can say that x of k is conjugate symmetric. From this we can say that x star of k is equal to x of minus k. Upon substituting k is equal to 2, we get that x of minus 2 is equal to x star of 2. But it is given that x star of 2 is 3 plus 2j. So x star of 2 can be written as 3 minus 2j. So from this we can say that for the given real continuous time periodic signal, if x of 2 is 3 plus 2j, where x of k corresponds to complex Fourier series representation, then x of minus 2 is 3 minus 2j.